Welcome to clickmyproject.com. Title of our product is 75 GBd INP heterojunction bipolar transistor MUX digital to analog control module for high symbol rate optical transmission. Abstract of our product is an ultra broadband 6-bit digital to analog converter has been designed and fabricated in INP-HBT technology. The digital to analog converter IC includes a 6:2:1 MUX and thus operates with the half rate clock. The digital to analog converter module is equipped with 1 mm connectors from its analog output to ensure broadband characteristics. The measured analog output bandwidth is greater than 40 GHz. 4-level pulse amplitude modulation signals with clear eye opening were measured at a simple rate of up to 75 GB. This multiplexer digital to analog conversion module has the widest bandwidth of any previous reported digital to analog converters and is suitable for high symbol rate optical transmitter. The 2:1 MUX multiplies the 12 half rate digital signals into 6 full rate digital signals. Then the digital to analog converters converts the 6 digital signal into an analog signal. This MUX digital to analog converter module has a half rate of input signals and the output will be full scale output amplitude. Now we are going to discuss about the flow diagram of our product. In our product we are using a different 3 modules to implement our product. They are retiming, multiplexing and digital to analog controller. In our product we are using a digital as an input signal and we are using 2 different input signals. They are digital input and clock input. Digital input have a half rate and then the clock input also have a half rate. The output of our product is an analog output. They are full rate of output. In retiming they are implemented by using a 12 different D flip-flop. In this D flip-flop input will be a digital input and then the selection logic will be the clock pulse. This output of the retiming D flip-flop is directly applied into the 2:1 multiplexing block. In this multiplexing the input will be come from a retiming and then the selection logic will come from the output of the phase shifter. In this phase shifter the clock rate will be applied to the input. The phase shift will be directly applied into the 2:1 multiplexing circuit. In this 2:1 multiplexing circuit block we are using a 6 different 2:1 multiplexing. This output of the 6 different multiplexer is directly applied into the digital to analog converter block. In this digital to analog converter block we are using a R2 to or ladder digital to analog converter core. This core will be produce the final output of our product analog signal. They are a full rate signal. Now we are going to discuss about the running procedure of our product. In our product we are using a Tanner EDA tool for simulation purpose. First we create a new design using this file option. File new to create a new design. In order to assign the design name using this option, assign design name in the desired path. After assigning the design name, click OK. After creating a new design, add the library files using this add option. Click add to select the library files path and then click OK. After adding the library files, all files will be added in this path. Logic gates, buffer, D flip-flop, inverter, mux, NAND gate. All logic gates are inside this logic gate library files. In this spice element, we are using spice elements, some voltage sources and etc. Devices using some extra devices, capacitor, resistor, inductor, the MOS devices, NMOS, PMOS also. MISC and source files, they are VDD, VSS, ground file and positive file. Spice command is an action unit. The print the voltage or print the power of our product also inside the spice command. After adding the library fields, now start the simulation using the cell option to create a new view. In order to assign our cell name, after assigning the cell name, click OK. In our product we are using a different 3 cells for design our product. They are retiming, multiplexing and digital to analog converter. The first block is an retiming. Click the retiming. In order to set up the simulation using this option, click setup simulation to add the library files using this path. Tanner EDA, Tanner tool 13.0 version, libraries, models, generic 0.25 library, and then assign the transient and Fourier analysis. They are how many time to start and stop. Assign the stop time and the maximum time setup and then the start time. Also, after assigning the setup spice simulation, click OK to start simulate this running process. Start simulation. This is the output waveform of a retiming. Expand this waveform using this expand chart option. They are also the output of the retiming process. The input will be the clock signal and then the output will be produced in the reference 1 to reference 12. They are all the output of the retiming. Now start simulate the second module of our product. They are multiplexing. Select the multiplexing to start the simulation using this start simulation option. This is the output waveform of a multiplexing. Expand this waveform using this expand chart option. They are all the output of our product multiplexing circuit. Selection is on a selection logic. Clock is on a clock input signal. The MUX1, MUX2, MUX3 also the 6 different multiplexing output signal. Now we are going to simulate the another one of a module. They are final digital to analog control module. Select the digital to analog control module to start the simulation. This is the output waveform of a digital to analog converter waveform. Expand this waveform using this expand chart option. The clock is an input clock signal. D is an input digital signal. V AN1 and AN2 is an analog output signal. V cell equals a selection signal of our product. Thank you for watching this video.